The following questions all share a unique quality. They all have numerical solutions, however, there are no numbers in the actual questions themselves. I like these types of questions because they suggest some inherent relationship between the parts involved. However, I'm not a fan of the names we have for them. I don't think there's a good, succinct name for them, so I decided to call them meaning of life questions, because a writer once wrote that the meaning of life was 42. I think it's necessary to define some rules for what makes a good meaning of life question. Here are 3 ways of phrasing the same question. 2 are invalid as meaning of life questions because they contain numbers or words such as double, which are too suggestive of numbers. The 3rd phrasing is legitimate and has a numerical solution. There are, of course, any number of questions that contain no numbers and have no numerical solution. These are also invalid. The 3rd condition is a relative one, and it's that we would prefer the questions to have some mathematical logic and not be mere trivia. These 6 questions are probably considered trivia questions. However, if we rephrase the first question, how many squares are on a chessboard, to how many squares of any size are on a chessboard, it can become a valid meaning of life question. How many 2 by 2, how many 3 by 3, how many 5 by 5 squares exist on a chessboard? One way of considering the solution is to think of how many of the little squares could exist as the bottom right square in one of the larger squares. As the squares get larger, fewer and fewer of them can fit on the chessboard. Through a process of deduction, we can see that the answer is 204. In order to limit the scope of this video, I've decided to focus on problems with 2-dimensional shapes. Let's start with area equals perimeter questions. We see that if the side length of a square is 4, the area and the perimeter are both 16. What about for a circle? What's the value of the radius that would have the area equaling the circumference? We'll get to the derivation of the area of an equilateral triangle a little bit later. The calculation for the area equaling the perimeter of an isosceles triangle is a little bit more tricky. What are the side lengths of a perfect right triangle with consecutive even number side lengths whose area equals its perimeter? We see that the solution is a 6, 8, 10 perfect right triangle with equal area and perimeter of 24. There are actually an infinite number of right triangles that will have the same area and perimeter. However, there's only one other that is a perfect right triangle in that all of the side lengths are integer values. What differentiates it from the 6, 8, 10 triangle is that it is primitive. The 5, 12, 13 triangle is a primitive Pythagorean triple. In order for a square to have the same area as perimeter, the side length is going to be 4. If that side length of the square is less, the perimeter is greater, and if it's more, the area is greater. So in order for our rectangle's area to equal its perimeter, one of the values is going to have to be greater than 4 and the other is going to be less than 4. It's also true that the lesser value has to be greater than 2. We see that the only integer solution other than 4 and 4 is 6 and 3. I'd like to stop and justify some of the equations I've written down. Let's consider the relationship between the diameter, which is double the radius, and the circumference of a circle. We see that it's a direct relationship. If we unravel the circle, we see that 3 and a little bit more diameters equal the circumference. With closer approximations, we eventually get to our value pi. We will get into the derivation for the Pythagorean theorem a little bit later, but for now I'm going to use it to justify the relationship between the hypotenuse and the side length of an isosceles right triangle. No matter the side length, the hypotenuse will always be root 2 times that value. Since the hypotenuse of an isosceles right triangle is also the diagonal of a square, I've decided to take another question. I mentioned earlier that we would look at how we calculate the area of an equilateral triangle. I've decided to break it into 2 right triangles with the height and half the side length representing the 2 short sides. That way we can calculate for the measure of the height, which we see as root 3 out of 2 times the side length. And that's how we get the area equation. There's a second method for calculating the area equation, which is worth taking a look at. You see we get the same answer. Now we're looking at equations where the area equals the side length. They have the same value. And now for these 3 shapes too. For the circle, it's what measure of the radius would make it equal to the area. And now we're comparing the diameter with the area, and with the square and isosceles right triangle, we're comparing the diagonal or the hypotenuse. I'd like to take a look at some of the properties of regular polygons. The square is the one with all right angles, and its interior angle also equals its exterior angle. They're the same. A triangle has no diagonals, but a square has 2, and a pentagon has 5, which is the same as its number of sides. I like this animation with the octagon, so I wanted to play it. Here we see some of the equations, and we see that the exterior angles all sum to 360 degrees. Here we see a triangle inscribed inside of a circle. If one of the side lengths passes through the diameter, then the angle opposite that side is going to be a 90-degree angle. But if we want to fill up as much of the circle as possible, it's best to use a regular polygon, or in this case an equilateral triangle. Here we see that formula for the area of a triangle again. We calculate the area of all three little triangles to get the area of the big triangle, and then simplify the ratio. If we try to see how big of a quadrilateral we can fit inside of a circle, we'll see once again that a regular polygon works best, or in this case, a square. We'll calculate the area of the square by summing four triangle areas. As our inscribed shape gains more sides, it can take up more and more of the circle. And here's the equation that tells us exactly what ratio and what percentage of the circle it takes up. You can use this formula to prove the area of a circle. I wonder if you can solve the question I've listed below. I'm going to solve one more question that will allow me to indirectly prove Pythagorean theorem. Here we have a large square, which is broken up into four identical right triangles with consecutive side lengths, and one smaller square inscribed within. What we're going to do is we're going to solve for the side lengths of this triangle not using Pythagorean theorem, but instead by comparing the areas of the large square with the areas of the four right triangles and the smaller square. These two areas are equal. We see we get one positive real solution and one negative non-real solution. We can generalize this method in order to prove Pythagorean theorem. We can prove Pythagorean theorem strictly from the area of a square equation and the area of a triangle equation. We see that the larger square equals a squared plus 2ab plus b squared. And the four right triangles and the small square combined get us 2ab plus c squared. When we compare the difference, we get a squared plus b squared equals c squared. I've included a challenge question below. That's it for the meaning of life questions in 2 dimensions, but I've added 2 for consideration in 3 dimensions. Here's also 3 additional meaning of life questions. I'm curious to see if you can come up with any of your own.